So now let's take a look at how to actually use tools to build a parser, because we've seen, yes, we can write a top-down parser very easily using recursions in our parser implementation here. Well, we've also seen that doing the same for a bottom-up parser is much more complex, and so we would like to use a tool that helps us with this, because, well, it's not very exciting to write a parser by hand, to be honest. So if you're interested in details, I've linked a nice video by a colleague from Imperial College, which compares writing a compiler to going skiing. So yeah, that's a very entertaining video, actually, of a colleague who spent many years doing research in compilers. And of course, we know that for simple tasks like scanning, we can use generators. So we've already seen yacc scanners, yacc scanner generators. And we know in a yacc scanner, each token is assigned a number, starting at 0 if nothing is specified. So this was one of the yacc scanner examples here. So what we do here, this strange notation of percent and curly bracket here means we want to include the following lines of C code here literally, so they're just copied into your generated C source code file for your yacc scanner. And we include the standard IO header because we might want to print out something later on in our scanner. And we declare an enum for our keywords of the language we want to recognize. So if, then, and if, and an int for declaring integers, and the end symbol. Then the corresponding percent and closing curly bracket indicates the end of our literal inclusion of C code. Then we indicate using these percent signs to yacc. Okay, the next section comes. So here we have our regular expressions plus the actions behind them to actually define the actions of the scanner. So we've seen that any of this set of a new line character, a tab character, a vertical tab character, or just a space character, so which is usually called just white space here. These just do nothing in our grammar because we just want to ignore them. And if we detect certain keywords here, so if, then, and if, or and, well, we return the enum values, so the tokens here actually corresponding to the keyword we read. And then finally, if we read a sequence of at least one or more decimal digits here, we return the information that this is an integer. So you have the declaration section here, you have percents, you have the next double percent section here, and after that you could write your main function, for example, to call your yacc scanner. So when you write a grammar like this, you see if you do a standalone yacc scanner, you have to provide an enum for this, for all the keywords here. If you actually use yacc in combination with yacc, and we'll see this in a bit, here that yacc will actually provide these tokens, numbers for these tokens in the declarations for us automatically, because yacc wants to know, of course, what it's recognizing as a parser here. So in the third section of our yacc scanner, we can write any sort of C function we like. So this is C code again. And usually for a standalone scanner, you write a main function here. So this main function, as we've seen before, reads tokens until it hits the end token here. So we've already seen that yacc is the yacc generated function implementing our scanner. So we call yacc separately for each of the tokens we want to get. So the token value is returned. And then we can, for example, in our simple scanner here, just switch according to the token value we've received, and then we reuse the values here from our enum that we've declared above. So if there's an if, we print, we found an if, and a break, so we can go through that loop again. If there's a then, we found then, and so on. Now if there's an int, we print something else, and we've already seen that, well, for if, then, and if, and end, it's completely sufficient if we just return the index of the token, so the type of the token. But of course, if we have a class of values like an integer or identifiers for variable names, of course, we also need to know the value of this string that we've read. So in case of an integer, well, The scanner doesn't know it's an integer. For the scanner, it's just a sequence of characters, and a pointer to this string, so to this sequence of characters, is automatically set in a variable that's called yacc-text. We've seen this before. So what we can do here is, whenever we find an integer here, we can say, oh yeah, we found an integer, and then use the %s format qualifier in our printf format string here to actually print the null terminated string, and this contains all the digits that belong to the integer we've just scanned. So, as you might have guessed, Lex and yacc were developed together by the people who also developed Unix at Bell Lab. So a yacc grammar is quite similar in its overall structure. So description files for yacc also have three parts. Some definitions here, then %% as a separator again, a couple of rules for our grammar here, and another separator, and then finally a set of auxiliary C functions or whatever C code you want to include. So this is the general skeleton for a yacc file, and this at first looks pretty similar obviously to a general skeleton for a Lex file. Now yacc understands a few more meta commands, I'd say. So as you might have guessed, everything that somehow controls our parser generator, like the scanner generator, starts with a % here. So we have a command %token that tells yacc, okay, in our programming language, so in our grammar, there is something, a token number, and we expect that our scanner, no matter if we use a Lex generated scanner or a scanner that was written by hand, would return this identifier here, so again expressed as a number in an enum or similar, if it encounters a number. Same for an identifier, but we could also just assign some values for certain tokens manually. So if we definitely want to have the number for our token word that's returned to be 4711, you can override this. Now you can also tell yacc which symbol to start with. So with most of our grammars so far, we just took the first symbol that was in our grammar here, so the one at the top as our start symbol, but this doesn't have to be the case. So we can actually indicate to our yacc parser generator which of the non-terminal symbols it should actually start parsing with. If we don't indicate it, then it still takes the first one as default. And like in Lex, obviously, you can also include C code, like header files, global variables, whatever you need, between the curly brackets here before you start the second section, which contains your grammar rules. So the next part obviously contains your grammar, and this grammar is very similar to the notation we used, and also this BNF notation we introduced shortly in a previous lecture here. So essentially you write some rules. Obviously you need to take some shortcuts because you don't have ASCII symbols, because all of this was done before Unicode came in, so you don't have arrows, for examples, for production. So you have to write it in a bit of a different way in order to be able to type it on a normal keyboard. And then finally, in our remaining section here, after the second separator symbol here, %%, you can write auxiliary routines. For example, you could write a main function. This is not automatically generated, so this main function could have the task of opening your source code file that was passed on the command line, and then just passing the first part of the source code file to our scanner, and then, of course, starting to parse. So how do yacc and Lex interact? So yacc parsers actually assume that there is a function yacc-lex, and we've seen this already. This is the Lex generated scanner function. And this yacc-lex function, can be generated automatically, or as I said, it can also be written by hand. Writing a scanner by hand isn't such a complex task, as you've seen already. So if you want to go for performance, because Lex scanners, because they're have this table overhead and everything, are not the fastest. So if you want a really fast scanner, some people actually write their scanners by hand, but let their parsers, because that's much more complex, be generated automatically by a tool like yacc. So our scanner function yacc-lex returns a value, And this value, as we've seen, indicates the type of token that's found, and this type is identified by an integer number. And for convenience, because we as humans want to be able to read this code like after half a year and not remember that token ID 42 was whatever an identifier, so we can give them symbolic names in order for us humans to be able to figure out what's going on. So anything else is passed in other variables. These variables are global variables inside of our scanner and parser, so they use them together actually. Of course, this is not good programming style, but since the yacc and yacc parser are designed to work closely together, I think it's perfectly okay, because it made the life of the parser and scanner generator writers quite a bit easier. So the other values are passed in yacc-text, which is the text of the recently returned symbol, and we have also a symbol called yacc-lval, which is a left value, which we'll talk about a bit later. So yacc, as you've seen, has this % token declarations here, so it tries to figure out integer representations, so integer IDs for each of the tokens. It actually internally does this by exactly defining an enum like we've done by hand. And what yacc does is it reads your parser.y file and it generates two output files. So in this y.tab.h file, among other things, it actually provides enums for the integer representations. So for our tokens, so for each token we identify, we have an association of a name of a token and an integer number. To generate this, we actually need to use call yacc with the option -d. Otherwise, this is just not generated. And the other file that's generated by yacc is y.top.c. So top just stands for table-driven browser. So this is the implementation. So this contains our yacc-parse function. And this yacc-parse function obviously is the function we'd use to try to parse an input file. So in order for yacc now to know about the token values here and the token names, yacc has to include this yacc generated y.top.h file. So what yacc does, it reads its input file scanner.l, describing the regular expressions making up our grammar. Inside of scanner.l, we add C code to include y.top.h, and then yacc outputs the scanner source code in a file yacc.yy.c. So yy, you see, there's a connection again to yacc, so they're designed to work together. So yacc actually provides yacc.yy.c provides the yacc function, and then you compile them and link them together. So you get some executable parser here, which then uses yacc and yacc together to maybe translate the source code to whatever comes as an output file. Okay, let's look at a practical example for yacc parser here. So this is an example that actually does something at least remotely useful. So this is a yacc parser that converts binary numbers to decimal. So we start with a file, we call it bindec.y, and we start by including literal lines of C code. So first we define a preprocessor symbol ydebug with the value 1. This tells our yacc generated code that it should actually output better debug information. And then we include some standard headers here, for example, for using printf. We also include some prototypes, and some of these prototypes are a prototype for a YY-error function that can print an error message. We include a prototype for yacc because we need to use this yacc generated function. And we also have the yacc-text, and that since this is a global variable of our yacc scanner, it's declared as an extern pointed to a character string. So this tells our linker later on that it needs to search somewhere else for a declaration of yacc-text. So we end our inclusion of literal C code, and then we start by this meta commands here, declaring our tokens here. And let's just say, well, we only want binary strings, so we have two tokens here, 0 and 1. So if you call yacc with the -d option, these both two tokens are just converted into token IDs, and you can look at it, and it would look like this one, enum y token type in y.tab.h, this generated header file. And this would just assign a value of 258 to 0 and a value of 259 to 1. why isn't it starting at 0 or 1 or something like this? Now this has a very simple use case, because in many cases when you have single characters as tokens, like a semicolon or an opening bracket, you just want to use their value as the token value. So what starting at 258 does is it skips all the valid ASCII characters and then some more. And so it's safely outside of the range of any valid ASCII character here, which would be between 0 and 127, or with extended values like 8-bit encodings for special characters like or A. Well, it would be 0 to 255. With Unicode, that's again a bit more difficult, but yacc scanners, yacc parsers, and lex scanners are not prepared for Unicode, so you should restrict yourself to ASCII characters if possible. So we have these two tokens, and we've seen they're just converted into two numbers here, and we tell our parser generator that n is our start symbol. And then we have a bit of a grammar here. So this will be implemented in our function yacc-parse by the scanner parser generator. So in our grammar, we start with our start symbol n, and n directly goes to L. So we've seen we added a specific start symbol, which then just resolves to one specific symbol again, because we have a bottom-up parser that is very happy when it just reads one symbol at the end of input. And as with lex, we can add C code as actions later on. So with lex, we mostly just added a return or something, and some meta information, for example, to count opening and closing double quotes for strings. Of course, we can add any C code, but this C code is a bit special here, because this C code includes symbols that your regular C compiler wouldn't be able to understand. So printf is of course standard. It prints a return, it prints %d, and then it prints something that's called $. And if you wrote this directly inside of your C code, well, obviously you'd get a syntax error, because that's not a valid variable or something name here. Now $, as you've seen, is the left-hand side. So the return value that's returned by a production that has something on the left-hand side. So what we do here is we go from our start symbol n for a number to L, and L might stand for left. So the left part of a number resolves to either another left part and a binary digit, which means what we do here is we take the left part, which comes from a recursion here, which is $1 here, times 2, and add our bit at the end. So we shift, because we read the digits from from right to left. So essentially we add the digits at the end, so the binary digits, so the remaining digits to the left must be shifted one place to the left, so they're multiplied by 2, and this value is returned. Now if we only read a single bit, then we just return the value of that bit here, and this single bit can be either a 0 here, which we identified as a token, or it can be a 1, also identified as a token. So we just return as the value of b here and $, whatever is the value of a 0 or a 1. Well, it should obviously be the number 0 and 1, because we're calculating with this. So all these $, symbols and $1 and so on are positional parameters in our grammar here on the left. So $2 stands for whatever is returned by the function that resolves our b here. $1 is whatever is resolved by the function that returns recursively in L here. And $, is essentially what we return as the value of, well, evaluating this production here, and then going one level further up in our recursion. So that's a bit strange at first, but you get used to it very fast, I'd say. So what else do we have to do? Well, when our parser encounters an error, it doesn't really know what to do with it. So we need to provide a function that enables our parser to print an error, and this is the prototype yacc-error. Doesn't return anything and takes a character pointer. So yacc-error, well, is defined here, and it just prints, well, the passed parameter here as a first string, and finally it prints the YY text, so the current token where our parser detected that something was wrong with our input. And our main function can be very simple. Our main function simply calls yacc-parse in an endless loop, and that starts parsing. So for a real compiler, of course, we would like to have additional functionality like opening a file and closing a file and reading stuff from a file, obviously. Here, yacc-parse. So all this parser here is by default reading from standard input, so just input from your keyboard. So what should the yacc-lex scanner that communicates with our parser look like? So this is bindeck.l for our yacc-lex scanner. This again includes standard I/O and standard lib. It includes the token declarations output by the yacc parser generator in y.tab.h. And it also has an external int variable yacc-lval, a left value variable here. This contains additional information about the parsed token. And this is a global variable in our yacc scanner, which we have to reference here. So this is again literally included C code. And this ends our first section. So here we start with a very simple scanner here. So if we read a digit 0, well, we set our lval here to 0. So that's our meta information here. It's a value, it's an integer, as we've seen. And return the information. This was a token 0. If we read the digit 1, we set this yacc-lval to 1 and return the information. Oh, it's a token 1. If it's some sort of white space, so a space or a tab character, we do nothing, so just a single semicolon here. If it's a return, we return 0 because that ends our binary numbers, because binary numbers shouldn't span multiple lines. And if we read something else, so a dot indicating any arbitrary character, we just return this exact character that we've read. And we've seen this scanner definitions, these regular expressions are evaluated top to bottom. So essentially this dot matches any character that's not a digit 0, a digit 1, a space, a tab, or a new line character here. And then finally, we include a function that's needed for more complex stuff like yacc-wrap, which is concerned with stuff like line wraps, and this just returns a 1. So you don't really need to understand right now what this is used for. So what you see is you need to have these values here. They're declared now in our yacc grammar here, so you need to know about them. You know about them because they're in y.tab.h, so you can just use them as symbols here because you have included their definitions. And in yacc-lval, you just set the information for our yacc parser, well, whatever meta information it is. So for numbers here or digits here, it would just be an integer, well, containing the value of the digit we just read, so 0 or 1. So the interaction works as follows. So we call yacc-parse in yacc from our handwritten main function here. Yacc, whenever it needs a token, calls yacc-lex. So it just first calls yacc-lex because in the beginning it doesn't have a token. And lex reads the input file and then returns the information about the token and also about the yacc-lval, which we should have set, and the yacc-text, which lex fills in automatically with the well, string of the characters making up the current token. So as you see, yacc-parse is called once, or also you can call it repeatedly until the end of file from main, and that's a user-supplied function, and yacc-parse itself then calls yacc-lex repeatedly until done. If there is a syntax error, then it calls yacc-error, which you also have to supply, and the function returns 0 if all input was processed, and it returns 1 if there was well, some error, syntax error in the input, so the parser has to abort. So yacc-lex in turn is then called automatically, repeatedly from yacc-parse, every time a new token is required by the parser. And this return value of yacc-lex is a recognized token, which, as we've seen, is defined in y.tab.h and generated from the yacc file token declarations and using the -d option on the command line. There are special token encodings, as we've already seen. So there's an end of file, which just has the value 0. Character literals, like a semicolon or brackets or something, get their ASCII value. And other tokens, as we've also seen, are assigned numbers larger than 127. And we've also seen additional information is passed back from lex to yacc using the yacc-lval, the value and the YY text variables here, the string of our current token. So here's going into a bit into details again about the grammar actions here we can write. We've already seen this. So like in Lex, we can specify C code for actions here in curly brackets on the right hand side after the production. And the parser generator actually includes these in the part of the code that's generated for the parser whenever the right hand side of the production has been successfully derived. So whenever we have a B here, we add the code just assigning $$ to the value of $1. And we've also seen that these special variables $$, $1, $2 refer to, well, essentially items in the grammar here. So if we take a look at our generation of grammars of parsers here, they refer to items on the parser stack precisely. So when we have a rule like this, L goes to LB, then whatever is returned as L is $$. The first symbol on the right hand side of the production is $1, the second is $2, and so on. Well, you've also seen for yacc grammars we don't have an arrow between our non-terminal symbol and our production, but we use a colon here. And if we have multiple productions for the same non-terminal symbol, we can use the vertical bar or the OR sign here, the pipe symbol, to actually indicate that there's yet another production here. So $1 is the semantic value of the first symbol on the right hand side, and well, for terminal symbols like 0 and 1, it stands for the value of YYLVAL that's returned by the scanner. For non-terminal symbols, obviously it has to go deeper here. And so for this, yacc would generate this line of C code and would assign YYLVAL is YYV stack pointer of -1 times 2, which is literal here, plus YYV stack pointer of 0. So it takes these two elements from its internal stack here, uses them as, well, integer, whatever values here, to calculate our new YYLVAL that's internally then returned. So that was a very quick introduction to yacc. There's lots of documentation on yacc and, example code and so on the net, but I think just using these, very simple declarations here and our small example, that should get you started with writing more complex grammars. Of course, all the theoretical problems behind this, like resolving shift, reduce conflicts, you'll probably stumble upon them, and, well, we'll discuss a bit later. For example, how you can use type information to resolve some of these problems later on. So data types and the related semantic analysis. So does the code that's syntactically correct, would this actually be a useful and correct program? These are what concerns us next. So for example, we will try to figure out if we try to assign an integer value to a character variable, which in some languages might not be allowed. So here's a number of references, and you see again, some of this stuff is pretty old again. So from 1984, there's an interesting paper on language-independent error recovery method for top-down parsers, so for L1 parsers here. There's yet another paper, which is very recent, so from 2019, about compiler error messages considered unhelpful. So they took an overview of the research on text-based programming error messages. So are these error messages actually useful? Do they help the programmer to identify what's going on? And finally, a paper by David Goldberg about what every computer scientist should know about floating point arithmetics, and this is more than 40 pages. But if you're really interested in this, so if you're going to do like high performance computing, simulation stuff in physics or other natural sciences, you should know a bit more about how computers handle floating point numbers and where the problems are in doing this. And we've given you a quick insight into this by showing you the problems that actually show up when there's a different order of resolving symbols from the left to the right or the other way around. So that's all for today's compiler lecture. Thanks for listening, and until next time.